So, hello everyone. This is Nandi from MIDAS, and today we would see how MIDAS Civil could basically ease the process of modeling and design for different kind of segmental bridges that you would usually encounter. Okay, now since this is a mass webinar, to avoid disturbances, I have put attendee mic on mute. If you can hear my voice, please raise your hand by clicking the button shown by number 2. Okay, everyone, can you hear me? Okay, I have enough raised hands. I'll just proceed. While giving the presentation, if you have any questions, please enter those in the box shown by number 3, and I'll try to answer as many of those as possible at the end of the session. If I'm not able to answer all the questions, we'll send a document with all the answers within a week. Okay. So before I begin with the presentation pertaining to segmental bridges only, I would just share a moment to, show the applications where MIDAS Civil could be used. It could be used for any kind of bridge structures, be it cable stayed, segmental, or any conventional bridge, steel girder and concrete composite bridge, a suspension bridge, integral bridge. It could even be used for structures which are not bridges, like for subway structures, tunnel structures, and even for dams where heat of hydration and all those kind of analyses are crucial. And coming to the advanced part, say for the bridges, specifically segmental bridges, analysis like contour and nose tip deflection would be necessary for incremental launching bridge. Similarly, staged construction analysis is necessary. Then 3D tendon and tendon loss, these could be easily done in MIDAS Civil. Then camber control graph, I would be showing this in the FCM bridge that we would be doing today. The dynamic nonlinear analysis, as well as design with AASHTO LRFD 2012 as well as Eurocode 2. Okay, so this is the agenda for today's online session. First of all, we'll just know that why FEA package is required for segmental bridges. Then what would be the typical modeling issues that would be faced if you are going for a finite element model? How MIDAS Civil would help you set up such model? Similarly, how it will help in precise analysis and results. Then how the automated design would be performed based on AASHTO LRFD. And finally, how quickly optimization could be done for an existing model. Okay, so we'll begin with why a FEA package is needed. So segmental bridges basically need to be carefully analyzed. Any such project would involve a huge sum of money, and any error or misjudgment in such kind of projects would be very costly in terms of money as well as life. So FEA, being one of the most precise solutions out there, need to be adopted for such segmental bridges. Then effect of pre-stressing needs to be carefully studied for this kind of indeterminate structure. Yes, of course, manual calculation is possible, but it would be very time consuming and the chances of performing error in that would increase. Then these kind of bridges take some time in construction. So the effect of variation in concrete strength with time, the losses that are going to happen, all of these need to be considered and simulated for a model that we are going to make. And such simulations could easily be done in a FEA package. The effect of erection loads also need to be considered, and this also requires a FEA package. So at what stage what loadings are acting, say for a FCM bridge, that is balanced cantilever bridge, if it is cast in situ, then the foam work load would have to be there. If it is a precast segment method, then you will have to consider the crane loads. So depending on the kind of construction method as well as the type of method adopted, these loadings would be changing and these have to be modeled. Now, segmental bridges are very large span, and hence seismic evaluation with refined methods become necessary. Now, when you are considering elastic foundation and soil structure interaction, so FEA is one of the most reliable approach for this kind of analysis. Okay, so now we will have a look at what typical modeling issues would be faced by any engineer while doing this. So first would be the depth of girder is varying along the length of the bridge. So the modeler will have to make n number of cross sections just to generate the deck model, which is quite time consuming. Basically, FEA implementation has critical certain issues due to which engineers do not prefer it, right? This being one of the major ones, and we'll just go through others as well. Another issue would be large number of tendons that are needed to be modeled. Modeling such tendons manually requires a lot of time and effort in any FEA package. Now, not only are these tendons supposed to be defined, but all these tendons would be activated activated in the model at different time based on when the stressing is going to happen in these. Then the individual construction stages have to be defined based on the method adopted for construction. Say for balanced cantilever bridge, again, it would be either precast or cast in situ, wherein the stages would be different. Similarly, for incremental launching method, the casting would be happening in bed and the loads applied would be different as compared to your balanced cantilever bridge. And similarly, a span by span construction is completely different as compared to the other two, though all are segmental bridges only. You know, typically speaking, for a balanced cantilever bridge, say if it is cast in situ, then though balanced cantilever, the loads acting would be your formwork, your concrete pouring, that would be your wet concrete load, and the eccentricity due to that much wet concrete which would be acting on your segment just before that. While for the same balanced cantilever bridge, if we are going for a precast segment method, then as it could be noted from the image, the crane would be actually acting on your pier table, and the moment due to the segment which is taken up would be transferred to your pier table only and not at the segment right before that. Okay, so for the same type of bridge, again the loadings would be different. And finally, temporary supports might also be needed to be applied in certain cases. So it could be concluded that the construction sequence, loading sequence, as well as strength of member at each stage play a crucial role in analysis and design of segmental bridges. Failure at any stage is obviously unacceptable, and hence it is mandatory to simulate the construction sequence to verify the same. Okay, so these were the difficulties that you would face. Now, how would MIDAS Civil make your life easy? So, MIDAS basically has several modeling tools which would make the process very quick and error-free. I'll demonstrate few of those later in the session, but for now, we'll just have a look at what it would do for us. I'll begin with the balanced cantilever construction method. So yeah, if you want to make this kind of a model, just use the FCM wizard, that is free cantilever method wizard, that is available in the software. What this wizard will do is it will generate the geometric model for the bridge. The 3D tendons needed throughout the span would automatically be generated. The construction stages for the same would automatically be generated, and the loads in these individual construction stages would also be applied automatically. Right, but usually what happens is whenever you use a wizard or something of those sorts, the modeling or whatever happens, it is completely unknown to you what process happened in between. But wizards in MIDAS are not black box. Each and everything that happens will be happening based on your input, and the generated model is also completely editable. So you could just make a general GAD kind of layout, and then if you want to change certain sections or you want to add your own unique loads to that, you could do that. You're completely free to do that. Okay, so this is how basically the balanced cantilever wizard looks like. At the top is the guide diagram based on which you'll have to make entries. So first of all, you have to define the material for girder, pier, and the number of piers that are there in your bridge. Okay. So as I was saying before, one is your precast method and another is your cast in situ method. Okay. So next input is well, your pier segment, the stage duration, and after that the method, whether it is cast in or precast. After that, you have to enter these values based on the guide diagram, wherein the FSM is the fully supported part, K1 is the key segment, zone 1 and zone 2 being the segments on left and right of the particular pier respectively, and so on. Say if your bridge is curved, then you could enter the radius for that as well. You just have to check mark on this radius and you have to give the radius, whether it is concave or convex, and that would be incorporated for the particular curve. Now that part was until the geometry of the bridge. After that comes the section definition. So you, as you can see, whether it is one cell or two cell, you just have to select that and enter the values again based on the guide diagram. But this is limited to your vertical webs. Say you have a particular section wherein your webs are inclined and certain other types of tapering are happening. What you could do is you could define the section using the section definition wizards that have already been given in MIDAS, and you could select type 2 over here. When this type 2 is selected, you could directly select those sections and the FCM wizard would be used with those sections to generate the entire model. And here, if you notice at the bottom, there is this include wet concrete weight. So if you're going for cast-in method, you'll have to select this include wet concrete. You'll have to give the crane load and what eccentricity you want to consider for the crane load. The number of tendons, as already said, for FCM bridge, those are very high. So you could give those over here directly. You just have to select your tendon and pre-stress. Again, specify the locations where your tendons are. Just give the tendon property and click on OK. With that, your entire model would be ready. So what we'll do now is we'll try to make a FCM model. So just hold on. Okay, so this is one of the base models that I have readied. So what I have done is I have defined the grade of concrete, the tendon material, the section for the pier, which I am taking as a rectangular 2 meter by 5 meter, and I have defined one particular tendon property. So the easier part in this being when you are defining the tendon property, you just have to select what tendon diameter is, how many strands are, and everything would be taken up automatically. Okay, so now coming to the wizard, you have to go to structures and FCM bridge. Okay, so select the material for girder, material for pier, stage duration, number of piers, and others. Now besides this, these are the default values. If you already have used this kind of wizard before and you want to generate a similar model, then you could save this wizard file itself and you can open it. Just click on open. So a wizard file which I had created before is already there with me. I can just click on that and all the inputs would come in the wizard automatically. Okay, but for now I'm keeping it as it is. I'll go to tendon. I'll just select the tendon property, top and bottom. Now, if you want to say modify it in the guide diagram, you can notice H2 and all these things are mentioned. If you want to change the tendon numbers, you just have to click on this tendon number over here and in which part, say N1 7. So for N1 location, there would be 7 tendons. For N2 location, there would be 3 tendons. So you just have to mention how many tendons you want at which location and it would automatically be added. So once you click on OK over here, it will take about a minute, but if you notice right now we just have given 3 material properties, 1 section property, and one particular tendon property. But with just that much data, my entire model with 144 elements, 248 tendon profiles is ready along with the construction stages. Now for the construction stages, let us say I'll just display the form traveler loads. So if I click on the display right now, it is looking like it's a mess. It is being applied everywhere on the bridge. But if you check it based on the construction stages, say for CS1, so it is applied at the edge of your last segment. Then again, when you change the construction stage, CS2, so the load is applied at that segment and the earlier load is removed. So this automatically is taken care of by the software itself. Even the tendon profiles. Okay. If I go to profile and display, okay. So only two tendons are activated at this location, but when I change, so more tendons are added up. So all these things are done by the software itself. So that's where the modeling will become really easy. Similarly, wet concrete loads are also applied. Okay, you could change the units anytime in between, kilonewton or whatever unit you want to switch to. Okay, now this part was related to the wizard. But say you want to do it without the wizard. So those options are still available for you. One is this automatic taper generation. So my saying that, okay, it is completely without the wizard is wrong. What this thing does is, if you have a typical section and you want to generate this kind of a tapered profile out of it, then you just have to give some basic inputs and it would be done. Now why this particular option was thought of, because at times what happens is, say for your particular box section, the tapering in the webs is happening over a length of say 8 meters, while the tapering of your top and bottom flange might be happening over a length of 4 meters, say for example. So to generate this kind of a tapering, this particular PSC bridge wizard was made. In this wizard, not only you could give this kind of tapering, you could even give the reinforcements for the varying sections as well. So that was for generating the sections. Then for the tendons, so you could enter the tendon profile manually, either in 2D or 3D input. You could the reference axis for these would be straight, curved, or element. Straight being if your profile is well, section is obviously everything is straight. Curved, if it has a curved profile, you could give that particular radius and the x coordinate would be taken along that curve. And element, say you have already entered the elements in a curved profile, you just have to select the element and x of the element will become the x of your tendon. Besides this, there is this typical tendon option as well, wherein say your particular box has 10 tendons. But for preliminary design, what you want to see is what happens if you are applying one typical tendon at CG. For initially for calculating how many number of tendons would be needed, where they need to be applied, we have to determine based on a typical tendon. So that option is also given. You just have to select this typical tendon over here and you could give its number over here. This number could increase to 10 and that single profile would be representing your 10 tendons. One other thing being, like for a box girder wherein your webs would be inclined, it is difficult to give particular inclined y coordinates or z coordinates in each and every case. So what you can do is you can just define one single tendon at the center, and this could be projected on the inclined webs on the left and right. Okay, so to do that, again I'll just go to the previous slide for a bit. There is this option given over here, projection. You just have to select this projection, give the angle of rotation, your web angle rotation over here, and at what distance it is. Okay, once you do that, in this way your webs would be projected on the inclined, your tendons would be projected on the inclined web. Besides that, you can also import the tendons from AutoCAD DXF file. Also for AASHTO, this effective width scale factor needs to be calculated for checking the stress. So there's a wizard available for that as well, which could be used with not just balanced cantilever bridge, with all kinds of bridges. That actually goes for the tapering method as well as the tendon definitions. Okay, so I'll just show a brief of these, the tendon, sorry, section tapering wizard. Okay, so this is my bridge. Okay, wherein if you notice the webs are inclined, not as in case of the FCM bridge wizard that we had used. Okay, so I have given some basic input data for that. I'll just apply the wizard and I'll show. Just open the existing one. Okay. So for now, I have only implemented the height variation in this, wherein you just have to enter the distances and dimensions. Say I want the height to increase from 2.5 to 5 meter in a parabolic shape. So I just have entered those kind of inputs for the three spans that are available over here, and accordingly the entire model would be generated. Why it takes a bit of time is, say this tapering is different for different regions, plus the reinforcements are applied. So applying that for the entire bridge takes some time. Initially, there was just one typical section, but now 81 different sections have been created, and they all have different ID numbers. Name being the same, it won't matter. You just have to go to the particular element, its ID would be displayed, and you could select that element. Okay. So in this way, with just a bit of input, my FCM bridge or incremental bridge, this could be any kind of segmental bridge, its geometry could easily be readied. Okay. Again, proceeding with the presentation. So I showed the FCM wizard a bit in detail. What I'll do is for the next wizards, I'll just show the kind of inputs you'll have to make on screen, and we'll proceed with the rest of it. So next would be your span by span construction method. So this is the way its wizard will look in MIDAS Civil. Just like before, you have to select the grade building material. Then you have to enter the span. So if you look on the screen, there is this 164, 2 at 197, and again 164 feet. Okay. So this basically means it has four spans of 164, four spans. First of 164 feet, then two spans of 197 feet, and then the span of 164 feet. Now this snapshot was taken in FPS system, but these units could be different. It could be meter, mm, it could be anything. That's not an issue. Okay, so if you want to go for a four span bridge, its input could be done in this way. Similarly, you could give the radius here as well. At which location you would like to give your fixed support bearing, fixed bearing, which location would be transverse bearing, that you could determine from here. And look at the guide diagram towards the left. So if your bridge has curvature towards your pier, then you can give it that way. Else you can simply put 1 over here for the curvature exponent, and it would be taken as a straight line. Similarly, you just have to provide the cold joint locations for span by span construction method. The cold joint locations are important, so you could input those over here, and the stage duration and member age. So again, that was for geometry. Then comes the section properties. Again here, just like the FCM wizard, you could either input these values, or you could import it from already defined sections. And finally, the tendon layout. Then for incremental launching bridge, again in this case, as you already know, the casting for the particular segment will happen in the casting yard, and which would be connected to the launching nose for the first segment. With the aid of pulling jacks, this would be pulled away, and in this way the entire bridge would be launched. Okay, so the loads acting in this case would again be different, where you want to apply temporary supports and everything you will have to do again. Okay, so the wizard for that is this ILM bridge wizard. Again, just like before, you have to define the material property, certain sections where you want to give the tendons for the flange. In this case, this option is in the wizard itself, where you want to give the tendons in the web, and what is the launching sequence for all these bridges. Okay, so this was how the modeling could be very quick and easy. If you'd noticed, the particular FCM bridge that we generated had several segments, it had many tendons, it had about 14 or 15 construction stages, and the entire model was generated in even less than a minute. So for these kind of projects, MIDAS Civil would be ideal. Okay, now for the precise analysis part. So as I said, these things would be time consuming. So variation in concrete strength with time needs to be taken care of. So you could consider this with CEB, FIP or ACI code, depending on which code you are using. All these database options are available, and the concrete compressive strength variation as well as the variation in elasticity, everything would be taken care of. Similarly, the creep and shrinkage also need to be considered. So for that also, just with a few basic input like your characteristic strength, your volume surface ratio, what would be the expected humidity, the creep and shrinkage coefficients would be generated and would be used in the model automatically. Then comes the secondary effects due to pre-stressing. Now these structures are indeterminate, and proper estimation of the secondary force developed due to the indeterminacy is necessary for these kind of bridges. So that is also automatically taken care of in the software itself. Again, say in a rare case, there's a chance wherein you are stressing the same tendon multiple times, or wherein there are stage pre-stressing, then the losses due to that are also taken automatically. As it could be noted from the image, the first one is tendon 1 and tendon 2. There are two tendons basically. So when the first tendon is stressed, there is nothing for the second tendon part. But when in the last image, second tendon is stressed, so the losses happening in the first tendon due to that are also taken care of by the software. Then the soil structure interaction. Now AASHTO has made SSI mandatory when working in soft soil. And also it is necessary to consider elastic foundation for seismic analysis, as it can cause change in demand even in earthquake. Yeah. So integral bridge spring wizard, which is available in the software, automatically generates the spring support for the pile or if needed for the abutment, and this formulation is done based on the BM-Lehne formula, which is widely used for SSI. So with this, you could get a better visualization of the load transfer as well as forces for the foundation design. So all that part was for the modeling and analysis. Now interpretation of the results is also important. So how will it help in getting precise results? So with many construction stage, what you'll get is loadings and the bending moments at different construction stages as well. So all of these, be it dead load, erection load, or tendon loads, creep, everything is available in the construction stage, wherein individual stages could be checked. Not only that, the result is not available at any one location. For the same section at several locations, you could get the results, and these are the predetermined 10 locations. You could add your own location to this as well, and the software will give you the stresses at that location. And that is not the only component. You will get axial force, bending moment, torsion, shear plus torsion, as well as principal stresses. The software also has something known as initial tangent displacement for erected structure. So for a FCM bridge, say it has already a downward deflection. So the new segment would be added with that already initially rotated part, and that displacement would be taken up. So that could be done by simply activating this small tick mark over here, and the software will consider that for the analysis part. Besides that, you also get a comprehensive tendon loss table. Stresses after immediate loss, elastic deformation loss, the creep and shrinkage loss, as well as the relaxation loss. These would be available at each and every individual stages, as well as in the final, that is after the construction stages are over. Also, it has a very detailed moving load analysis system. You could define your own vehicle with multiple axle, or you could go for the standard vehicles that are already given for AASHTO along with its dynamic allowance factor and everything. Besides that, input for lane support negative moments and reactions. These are also automatically taken up by the software, wherein you just have to give the girder group where you are expecting the negative moments. So in this case, what we'll do is we'll just give the entire bridge, and automatically wherever the negative moments are coming, the provision of AASHTO of 90% reduction based on 2 trucks would be applied, and that bending moment would be shown. Similarly, say if you are not actually doing a box girder bridge, you are doing a I girder bridge, PSC I girder bridge or something, then in that case, the traffic lane, which is defined only in a single line, the vehicle has certain width of say 2 meters and your traffic lane might be say 3.5 meters. So what the software will do is the software will automatically move this 2 meter vehicle, 2 meter width vehicle in the 3.5 meter lane width, and whichever vehicle position is causing the worst bending moment for a particular girder, that bending moment would be shown for those girders. So you'll have to design for that. So this way your headache of checking the which particular vehicle position is causing worst bending moment for the girder is taken care of. Automatically the software will do that, and you just have to design for the final bending moments that are shown. For bridges like free cantilever, balanced cantilever bridges, the camber control becomes necessary. So what is the camber at each and every stage, that could be shown by the software. Besides that, if these camber needs to be applied at the time of construction to make the final deformation as 0, then it could be taken up by the software again automatically by just selecting this apply camber displacement to CS. Once you check this, these displacements would automatically be applied at the time of construction, and you'll be getting the final result. Besides that, detailed seismic analysis which needs to be performed, the software has several tools for that as well. The response spectrum analysis, the pushover analysis, boundary nonlinear time history analysis, as well as inelastic time history analysis. Okay. So now proceeding to the design part. Analysis is done, result interpretation is done. What we need at the end is design. So the software will perform these ultimate checks and service checks based on AASHTO LRFD. The stresses at construction stages, stresses in pre-stressing tendons, for service loads, principal stress, as well as the crack width would be checked for the service checks, and the ultimate checks would be for flexure, shear, and combined shear and torsion. So with certain parameters selection, you would get quite detailed result tables, as well as you could see on the left, the detailed Excel report would automatically would also be generated once you click on the generate report part. Okay, now until now was the designing. We can do the design, right? But whether it is over conservative, whether it is unsafe, we need to optimize it to the point, because these projects are very costly. So for a typical post-tension box girder design process, it is something like your preliminary design and static loads, moving loads would be done in certain package. Then the seismic analysis is again done somewhere else. Then the detailed design input are again made in the initial software package. And finally, it is checked for your service as well as ultimate strength, and the final design for pier or foundation and soil structure interaction are done. This was the typical process earlier. So what are the drawbacks of doing it in that way? Now, what happens is longer time is consumed for the same project completion. there would be n number of model files in different softwares for different phases. So that is a huge amount of data, and chances of data loss are also there. Plus, certain people would be very convenient in certain softwares while others might not be. So you would require more manpower to do the same work. And the inefficiency in design would be high in this way, which would lead to higher conservatism. So final outcome would be lesser projects would be completed in a more longer time, lesser degree of competency, repetition of work. So for the same person who is doing say foundation design, he would be bombarded with different foundation designs. That's it. He has nothing else to do. So that's a repetition of work would be there. And finally, it would lead to monetary loss. Now, if all these things are done in a single software package, then the benefits would be there would be only one model file for all the construction stages for all the different types of analysis that you want to do, be it static, moving, dynamic, SSI, any kind of analysis. It would be only one file. The design checks, constructability checks also would be checked in the same, and the precision would be very high because when the same person is working on a same software, he would be very used to that and he could easily pick out where even the mistakes might be, if at all done by anyone. So the final outcome would be more projects would be finished in a lesser time, higher competency, you could easily compete in the market, no repetition of work, different bridges meaning completely different kinds of loadings and different outputs to handle. And the final outcome again, there would be much more monetary gain as compared to the initial approach. Besides this, what MIDAS Civil offers is several automatic bridge generation tools, better and very easy graphical user interface, improved graphics with CAD effects, which is quite necessary nowadays, and detailed stress check, peer crack analysis, and even fiber modeling if needed. Okay, so that was me just saying of these things are possible, but yeah, no one would believe unless these things are done actually, right? So what I'll try to do is I'll just try to optimize a bridge for certain parts. Okay, and I'll just show you how easily and how quickly these things could be done. So what we would be taking up is a balanced cantilever bridge, three spans. Its length is 290 meters, width about 15.2 meter. We would be using the balanced cantilever bridge wizard, the FCM wizard, and we would be using AASHTO LRFD codes. So for the preliminary design, what we'll do is we'll define the material properties, use the proper auto-generate wizards, which would be FCM wizard, and specify the parameters for span and section. So I'll just do that. Okay, so we'll select FCM bridge wizard and our inputs are default. I'll just change certain things. And we'll click OK. Well, the model would automatically be generated. Okay, yeah. So once the model is generated, we'll perform its analysis quickly and then we'll put it up for PSC design. I think, yeah, that would be better. Okay, so the model has been generated and we'll just click on this to perform the analysis. Okay, so the analysis for this bridge will take about a minute. So in the meantime, if anyone has any questions, just type those and I'll be glad to answer if I could. Okay. Seems like I'm doing pretty good presentation. No questions so far. Okay, so this is how once you perform the analysis, it will show you how much the analysis has been performed and how long basically it will take to finish. You could judge from the speed itself. If this kind of analysis has to be performed in certain package, which is not a FEA thing, the analysis for this kind of bridge will take long time. If you notice, once the analysis started, it was finished within just 19 seconds. Okay, so now this was the analysis part. You could check the results anytime. Say we go to forces, beam diagrams. Okay, yeah, we'll have to define a load combinations first. So we'll go to results, load combinations, concrete design, and we can auto generate the load combination. So based on AASHTO LRFD 2012, okay, if I want to generate the load combination, I just have to select it, enter certain parameters, that is for components and attachment, what would be the load factor I want to check and all, and the box is too big, right? So it might not fit in your screen. So what you can do is you can just click on this small minimize button over here and the part of box would be minimized. So that way it could be used on a screen with any resolution. Okay, do that and click on OK. So the load cases based on that have been generated. Okay, so now if I want to check the result for the load cases generated, I could check the result. You do not need to perform the analysis again when you are giving the load combinations. These are applied in the post analysis stage. So with the same things, only the factors would be multiplied and the results would be available to you. Okay, I have a question over here, but sir, I'll be answering that at the towards the end of the session or when we are performing another analysis. Okay, so if I say legend, I'll just switch the units to kilonewton meter and apply. Okay, so what kind of bending moment is going to happen for which component could be checked? You could even check the stresses at different locations as I said before. Okay, so now moving on, we'll go to the PSC design. So I'll just click on PSC, AASHTO LRFD. I'll just select the parameters. Once I click on parameters, these things are made available to us, right? Now, as I said, in this case, we are going for a segmental bridge. So construction type has to be segmental. If you are not going for segmental, you have to select this non-segmental over here. The types of tendons, what are the exposure class you want to consider for the crack width. You just have to select those and what output you want to see. So for now, I will just be selecting all. Okay, so you can just click on select all and okay. Okay, then the design material. What we had defined was the grade of concrete, but what would be the grade of reinforcement in this we had never defined. So we have to click on the particular material, sorry, select the grade and we are done. So this has to be done for both the cases. Similarly, we have to give the output positions, that is at which section we want the results. So in this case we would be giving it for the entire girder. Then there is this segment assignment feature. So AASHTO specifies that the stresses at the joint would be different as compared to other locations. When you are going for a FEA package, it might be that you have generated a 1 meter length segment, say, but practically speaking, these segments might be say 3 meter long. So unless we give a segment assignment, the software won't know where the joints are. By default, it will consider the joint at each and every segment location. Okay, so if you want to avoid that, you'll have to give PSC segment assignment. Okay, similarly, the allowable stresses. So based on the load combinations that we gave, what is the service limit 1 case and what is the service limit 3 case, the software will take. You could add other cases as well. Okay, so once all this is done, you just have to click on perform design. Okay, so now I'll just have a look at the question. Yes, sir. So this sir is asking that in moving load, is it considered, does it consider transverse moment or movement of vehicle within the lane for creating most critical load effect for different ribs? So yes, what it does is, say the lane width is 3.5 meter and the vehicle width is 2 meter. So initially it will put at just edge of the lane, then it will move the vehicle from say 0 meter distance to 3.5 meter distance along the width. Okay, so it will check which vehicle position is creating the worst bending moment for that particular rib, and the output given would be for that rib only. Okay, I think we in this case actually we haven't given output position. So I guess we'll just perform the analysis again after this is done if the results are not visible. One more other feature would be, say you have provided the reinforcements and tendon for your particular section, right? So it has certain ultimate resisting capacity. So what is the capacity and how much of that we are actually using? The software will show us that as well. So there is this PSC result diagram option. I'll just click on that. Flexure 1 for all combinations. If I say apply, okay, so what is the flexure that is resisting capacity and how much is happening? Okay, so it will show us. If I click this solid, so this green line is the resisting capacity, while this solid filled line, that is the load which is acting on your section. So you could verify these as well. If I go to result table, say check section at service stage. Okay, so it is failing at certain locations, right? So what could be done is, well, it is failing in tension. Yeah, it is failing in tension. So what needs to be done is we'll have to increase the section size. Okay, we can modify that. So we'll just go to structure again. I can just undo the already existing model that I used. Okay, or I could open a new model as well. That is not an issue. But once it is done, what we'll go is we'll just give the section a bit more height. So the m by z component would be reducing. So p by a minus m by z would obviously be under compression rather than under tension. And what we'll do is we'll actually reduce the number of pairs as well. 4 pairs, the time in generating the model is increasing. Okay, so say for this, I'll just check whether it is done. Yeah, it is done. Okay, so I'll just go to FCM bridge wizard, reduce the number of pairs to 2. What I'm doing is I'm increasing the section height by a bit. So I'll go to open. No, this is the existing one. Okay, so say H2, instead of this 2.286, I'm making it as 2.4. Okay, and width I'm reducing by a bit. Say B2, I'm making it as 0.5. Okay, and I say okay. So see, the number of spans reduce, so automatically the generation time reduce. Okay, so this is done. We'll just again create the load combinations. Sorry. concrete design, auto generate, AASHTO LRFD 12 and okay. Okay, so the load combinations have been generated. We'll perform the analysis. Okay, in the meantime, I'll see if I have any more questions. Okay, what do you mean by wet concrete load? So basically, sir, if say the method for balanced cantilever bridge construction is cast in C2, so what will happen is your form traveler would be there, and in that your wet concrete would be placed. So based on the cross section as well as what is the length of the segment, the weight of the wet concrete or the green concrete would automatically be calculated, and that vertical load as well as the moment would be applied to the existing section. Okay, I'll just put it for PSC design as well. So these inputs are all very easy and could be very quickly done. So the modifications required for checking what particular particular modification is doing, the time required, it becomes very less. Say the design position. Okay, so I want it for my bridge deck, so I'll just select the deck elements. I'll click apply. Similarly, my output positions, I'll just select the deck and apply. Okay. I am considering each segment to be individual, so I'm not selecting that for joint. The allowable stress cases, and I'll click on perform design. Okay, so I have one more question. So if we import section of girder from AutoCAD, can we still do the automatic design like strength check, etc. in model, or do we need to assign cross section in model itself to do design in software? No, yes, you can do it from the AutoCAD as well. What actually matters is the parameters that have been provided, right? You have provided the section size, so I and all would be calculated in the software and that would be taken up, as well as the length for the design and all. In fact, there is a small input for that needed if you are using the SPC, but yes, you can perform design for that as well. Okay, so in the meantime, while this designing happens, we'll just move to the PPT and continue. Okay, so this is the preliminary design wherein we define the material, auto-generated the wizard, and specified the parameters for span and section. Then the static load as well as the moving load analysis could be performed. That is the dead loads which are already defined, the self weight and all is already there. The tendon profiles which have been defined, and if you want to add more, you could do that. The rebars have been defined in this section, and the moving load could be given as per AASHTO LRFD. We are not doing this right now as we are a bit short on time. Okay, then design checks. So auto load combination as done before. Then manual definition of the support, but that has already been done. And we have to check the strength and service limit case. We defined the material and the design performance is in progress. Okay. So we'll see if the analysis is done. Okay, so analysis has been done. Now again we'll check what is happening for the service load case. So you see, whatever was failing in tension is now not failing. So anytime if any section is failing at any location, it would be shown as NG over here. So for example, in this case, what I have done is I just verified it for the particular cross section stresses at service stage. If I'm checking at some other part, say for first itself, so in construction stage itself, say it is failing at several locations, so this is unacceptable, right? So modifications need to be done to take care of this as well. The stage duration would have to be increased and the concrete strength will automatically increase, so that would be taken care of. So these are the kind of modifications we are talking about. We can check the initial thing, we just have to make a minor modification, and the entire model along with the analysis would be readied in a couple of minutes. Okay, so moving on with presentation. Okay, this is done. So what we did right now was we modified the cross section. You might, add more tendons or move the tendon a bit. That is all up to the designer. And you could go for a safer design. So what are the benefits by using this approach? So as you already noticed, the model is auto-generated and it acts as a design guide to the engineer, where what modification needs to be done could be easily understood by the engineer. It's quick and error-free. For the code sections that have to be generated and everything, you don't need to calculate anything. Everything is done within the software, and the tendon definition also happens automatically. As you noticed, the model could be easily modified. I just changed its section properties and I have two models ready with me which I could compare. It saves up a lot of time and hence more projects could be done quickly. And it has built-in design checks. All of this is done in the same file. Okay. Besides this, the time dependent behavior could also be added. Soil structure interaction. So what we did was we just made the deck and the piers, but manually you could add the pier caps below this, the pile cap below it, and the piles could be added. These piles could be given their own springs and the analysis could be performed. Response spectrum based on AASHTO is also available, that could also be applied, and the construction schedule to suit specific site conditions could also be used. Say you have performed certain design but certain part of the bridge is constructed, the project hits a bit of slump and the construction is delayed by a couple of months, say, so you need to re-verify, and these kind of things could be very easily done if this kind of FEA package is available. Then construction stage analysis as well as the erection sequence could be easily checked. The model is generated, which the model generated automatically takes care of this sequence. The design check while the construction stages could also be taken care of. We could get the camber. Yeah, I forgot to show the camber. I'll just show that. Okay, so say for this bridge, if I go to results, camber, and FCM, since ours is FCM bridge and FCM graph view. So I'm taking for the summation, that is your dead load, tendon primary, everything included. What is the final load for the construction stage, that I am taking, and okay. So this kind of a graph is popped up. So where you see this kind of down drag, this is basically your key segment, and at these locations, so it is almost zero, those are your peer locations. So camber of what height as well as at what node needs to be applied could be easily checked, and this graph, it's quite big, right? So you could zoom in on a particular length and it will show. Moreover, for the same node it will give you two values. So these two values are like with formwork what would be the camber, and once the formwork is removed what will be the camber. So that's why these two values are shown. Okay, so this would be your camber control graph, and this camber itself could be applied in the model and it could be reanalyzed. And we can check force in each stage and modify the force in tendon if needed. Okay, so again, at the end, what we are looking for is benefits as compared to our existing methods. So the benefits are auto generation, single model file for everything, as said before. Design optimization, that is the most important part. You could optimize your entire model in the same file, and you do not need to learn different softwares or different graphical user interface. Checking also becomes very easy. The detailed design including your existing static loads, moving loads, as well as your advanced analysis like soil structure interaction, time dependent material, everything could be done. Seismic design could be done, and performance based analysis like pushover analysis could also be performed in the same file. Moreover, It has the capacity to design RC sections, steel sections, everything. I'll just show as in where these are available. So this was the PSC part, right? But say you want to design your RC pier, so you could go to design, select AASHTO LRFD, enter the parameters here, then design either a beam or a column. Okay, so RC design and steel design as well as the composite design, well, that is for Eurocode, AASHTO as well. So these things could easily be done in the software. Besides that, you could check the pier for cracking, obtain moment curvature diagram, and if you want to go for a very detailed analysis, you could go for fiber section analysis. Okay, so this is the kind of output that you would get. Besides that, actually, MIDAS Civil also has a general section designer. So say if the pier has certain irregular shape, which is not available in the software. So for that kind of irregular shape as well, you could perform design using MIDAS Civil GSD, that is General Section Designer module. One of the major drawbacks of most of the packages out there is what happens inside is a black box. We are not aware of that. So for MIDAS Civil, what we have done is we have created a design guide as well, wherein a step-by-step guide of what is the theoretical part as well as what is being done in the software is shown. So if you need a copy of this design guide or if you have any other doubts, you could contact us at this email ID or the phone number provided below it. So I hope you all enjoyed the session, and now I'll be taking up any questions there are.